As it stands, this integral has no antiderivative. The classic way to get around this problem is by using a clever symmetry trick from physics. In this video, we're going to discover that symmetry trick and solve the integral along the way. Here's the graph of e to the negative x squared. Notice that if we look to the left, it looks no different than if we were looking to the right. In other words, it has symmetry. Right now, the integral is asking for the area under this curve by integrating along the x-axis, which is only in one dimension. Now, the discovery is this. Whenever there is symmetry present, it usually means that there is a smarter perspective hiding somewhere in another dimension. In our case right now, there is symmetry present, but the one dimension that we are in is not helping us, so we might try to go up to 2 dimensions. Transforming into 2 dimensions means that instead of the integral giving us the area, it will be giving us the area squared, which is just the integral multiplied by itself. This might seem weird at first, and it is totally reasonable to think that the integral of e to the negative x squared is not the same as the integral of e to the negative y squared. But if we think about it, the integral of e to the negative something squared yields the same area no matter what that something is. Here is our new function. Notice that it looks the same no matter which direction we are looking in. In other words, it has rotational symmetry. Right now, we are in Cartesian coordinates, but this function has rotational symmetry. Whenever there is rotational symmetry present, it is not appropriate to use Cartesian coordinates. Why? Because if something has inherent curvature, then we have no business being in a coordinate system that is constructed with right angles. Let's switch into polar coordinates. First, we combine the exponentials and see that x squared plus y squared is just the radial distance from the origin. Stepping a distance dx along the x-axis and a distance dy along the y-axis covers an area dx times dy. In polar coordinates, stepping a distance dr in the radial direction and then opening up by d theta causes us to step rdθ in the theta direction, covering an area rdrdθ. Here is our new integral in polar coordinates. We can see that the x squared plus y squared became r squared by Pythagoras' theorem, and the Cartesian area element dxdy became the polar area element rdrdθ. First, we can solve the angular integral to get a factor of 2 pi. And now we are just left with the radial integral. We can notice that the derivative of e to the negative r squared brings along a factor of negative 2r dr with it. The rdr part is already included in the integrand, so we would just need to divide out that extra negative 2 bit. And now we are done. We can just use the fundamental theorem of calculus and then clean up, and when the dust settles, we end up with pi. But pi is not the area, it is the area squared. It is what we get when we transform our original integral into 2 dimensions and then solve it. To transform into 2 dimensions, we squared our integral, so to get back into 1 dimension, we need to do the opposite thing, which is to take the square root. And we are finished. The area is the square root of pi. In the wild, e to the negative x squared is not usually found naked, so it is worthwhile to find the same integral, but this time with an extra factor of alpha inside the exponential. The steps are exactly the same, and you should see that it is the square root of pi divided by alpha. Now you're able to find the area of e to the negative x squared no matter what clothes it is wearing.